This is a review for sections 4.1 through 4.3 and 4.8. In 4.1, we classified triangles by angles. If all of the angles in a triangle are less than 90 degrees, the triangle can be called acute. In Chapter 1, we called individual angles acute. Now we can call the entire polygon acute. A similar thing for right triangles. If one angle in the triangle is 90 degrees, we can call the entire triangle a right triangle. Or if one angle in the triangle is obtuse, meaning it's greater than 90, we can call the entire triangle obtuse. We also classified triangles by side lengths. If all the sides are the same, we call that an equilateral triangle. If two side lengths are the same, we call that an isosceles triangle. And if no side lengths are the same, we call that a scalene triangle. The last thing from section 4.1 is an equiangular triangle, and that is when a triangle has three congruent angles. An equiangular triangle has to be an acute triangle because they have to all be equal to 60. In 4.2, we covered the triangle sum theorem, which says that the sum of the interior angles of a triangle is 180. So if I took these three angles and I add them up, every time I will get 180. So if one is missing, I can figure out what it is by taking 180 minus the other two. Also in 4.2, we said that the acute angles of a right triangle are complementary. So instead of taking 180 minus, I can take 90 minus to figure out the other of these two acute angles, because angle 1 and 2 are always going to add up to 90 degrees with a right triangle. A corollary of the triangle sum theorem: if a triangle is equiangular, that means that each angle is going to be 60 degrees, because they have to be the same and they have to add up to 180. In 4.2, we covered the exterior angle theorem, which has to do with the relationship between these two interior angles, 1 and 2, and this exterior angle, 4. So 3 and 4 should form a linear pair for this to work, and if that occurs, then I know that angle 1 plus angle 2 is equal to angle 4. The third angle theorem states that if two angles of one triangle are congruent to two angles of another, the third pair are also congruent. This has to do with the triangle sum theorem. If they all add up to 180, and two of them are the same, the third one has to be the same also. In 4.8, we looked at some specific properties of isosceles triangles. If the two legs are the same length, then the base angles also have to be the same. And the same is true in reverse. If the base angles are the same, then the legs have to be the same length. And there are similar relationships for equilateral and equiangular triangles. If the side lengths are all the same, then the angle lengths are all equal. And if the angle lengths are all equal, then the side lengths have to be the same too. In 4.3, we talked about congruent triangles. Congruent triangles have corresponding angles. So if triangle ABC is congruent to DEF, then the angles match up. Angle A is congruent to angle D. Angle B is congruent to angle E. And angle C is congruent to angle F. The actual diagrams might not totally match up if one of the triangles was rotated. We pay attention to the order of the letters. Congruent triangles also have corresponding side lengths. So if triangle ABC is congruent to DEF, side AB is going to match up with side DE. So in this diagram, the triangles have been rotated, and I can mark those side lengths as congruent. And a similar thing with BC and EF, and CA and FD. In this section, to prove that triangles are congruent, we had to show that all of the angles and the side lengths correspond. As we continue into the rest of Chapter 4, we're going to learn some congruency shortcuts, how to determine if triangles are congruent without knowing that all of the side lengths and all of the angles are equal.